Hello, welcome back to Engineering 201 Electrical Fundamentals, and I wanted to today go over the second examination, or the second practice examination. Again, the same comments that I made before doing that a while ago on the first practice examination. If you haven't attempted this exam on your own, I'd highly recommend that you printed it out. You can go to the website, and I put the link to the website in the description of the video, but go to the website. On the left of the website, you'll see the class Engineering 201. If you go there, there's a subpage under that that says Sample Examinations, and you can print out the sample examination with or without solutions and give it a test on your own. So again, I highly recommend that before you watch this video. If you've done that and you just want some confirmation, or you're struggling on a particular problem, then hopefully you'll find this video useful. So I'm going to go ahead and get started with this. I've tried to blow these problems up fairly large, but they may still be a little bit difficult to see on video. As always, I'll post the PDFs, and you can also get that through the website. So with this, we've got problem number 1 here. It asks what's the Thevenin voltage and what is the short circuit current. So we're given the circuit. The first thing that we notice right off is that we have a dependent current source. So that means that there is no shortcut. So no matter how much of a hurry we're in, how much we'd like to use the shortcut, we can't use the shortcut. There is no shortcut on this one. We're going to have to go through this, find the open circuit voltage, and find the short circuit current, which incidentally are the two problems here, and continue on. So to do that, why don't I put some currents in here? I'm going to say that this is I1. I'm going to say, let's see, we were given that this is I've cut off the problem description, but if you go back and read it, I believe this was 10 volts. This was 1K. That this was 1K. This was 1K. And this is also 1K. I got a deal on 1K resistors. I'm going to say that this is I2. And I've got IX there. I think we're okay. So we're going to look first for V open circuit, which would really be equal to this IX times 1K ohm, right? Okay. So if we notice this, we have an essential node, which is essentially this entire node up here, indicated with V1. V2, this is not necessarily an essential node. So we have an essential node here, and we have an essential node here. We'll take that one as the ground. So we'll write Kirchhoff's law then. We can say that we have I1 plus, that's that current there, I2, that's also leaving, plus IX, and that's going to be equal to, so that's leaving, and that's leaving. It's going to be equal to this that's going in, which happens to be 2IX. So we tidy this thing up. I1 plus I2 is equal to IX. Make my substitution. So I need to find the voltage that way, which is going to be minus 10 plus V1 divided by 1K plus I2. That's easy. I just have to go that way, which is going to be V1 over 1K is equal to IX. Now IX is going to come down and go through both of these, because this is open over here. So it will be V1 divided by 2K. So if I multiply everything by 2K, so multiply by 2K, I come up with 2V1. Let's see, minus 20 plus 2V1 is equal to V1. So we'll get collect up the V1s. I've got 4 less 1 is 3V1 is equal to positive 20 on that side. So V1 is equal to 20 over 3. Well, what good is that? Well, we can come up here and say that IX, didn't we say that this IX was V1 over 2K? Yeah. So if maybe I'll just continue working down here. I'm going to work this problem number 2 on a separate page. So I can say that Ix is equal to V1 divided by 2K, which gives me 20 over 3 divided by 2K, which would be what, 40 over 3 milliamps. No, 40 over, going the wrong way, 10 over 3, right? Sorry about that. 10 over 3. And then I take care of the K's by saying milliamps. Okay. And then we agreed the reason we were finding Ix is to get this. So we can say, so therefore, V open circuit is going to be equal to Ix times 1K, which is 10 over 3 milliamps times 1 k-ohm. Millis and killies cancel, and I end up with 10 over 3 volts, which would be 3.33 volts. Do we have an option for that? Yeah, right there. Option A, 3.33. Good. Okay. So, pretty straightforward. Had we not had this in here, then once we've got the V open circuit, we could use our shortcut, shorting out our voltage sources, opening our current sources, and get our equivalent resistance. But we can't use the shortcut, so let's go on. And say again this was 10 volts, 1K, 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 1K. And now when I short this across here, that becomes I short circuit. So we've already got this one done. That's on page 1. So we're working on this one here. We'd like I short circuit. Now, no current is going to go through 1 k-ohm resistance when it can go through a dead short. So that effectively removes this. No current's going to be going through that. So I could effectively remove that, and then I end up with something like that. If I put the same currents in here that I did last time, I could have I1 and I2, and then I've got Ix. So if I do Kirchhoff's law, I can say that I have I1 plus I2 plus Ix is equal to 2Ix, this current going in up there. So tidy that up again. I1 plus I2 is equal to Ix. I get exactly the same things that I did last time. V1, at least for the first two terms, V1 minus 10 over 1K plus V1 over 1K. And you may choose to just go back and go back to these equations from the first one and modify them, or start from scratch. With going back and modifying them, you run the risk of not getting everything fixed like this last term. This should be a little bit different. Instead of V1 over 2K, now I really have this point, which is ground, is the same as that point, which is ground, because this is short. So I really just have Ix is going to be equal to V1 divided by 1K. So you have to be careful with that. So now I'm going to multiply this thing by, what, 1K? So I get V1 minus 10 plus V1 is equal to V1, or V1 is equal to 10 volts. And why did I want that? Well, I know because I've taken this resistance out here that Ix is equal to I short circuit, isn't it? So Ix, which is going to be equal to this one right here, V1 over 1K, so I have 10 volts over 1K, which gives me what, 10 milliamps? 10 milliamps. So I've got 3.3 volts for my open circuit. I get 10 milliamps. Do we have an answer there? Yep. positive 10 milliamps. Now, our last answer, we answered this as positive 3.33. If I had a positive voltage, I have to have a positive current because I can't tolerate a negative resistance. So we know automatically that that's no. So answers A and B so far. Then, going to part number 3, what's the Thevenin resistance? Well, we know that the Thevenin resistance is now the ratio of the open circuit voltage. So our Thevenin is equal to V open circuit divided by I short circuit. Had we been able to use a shortcut, had this not been this guy not been here, and I could have used a shortcut, you could have got this directly, and then you would have only had to find V open circuit or I short circuit. But we didn't have that, so we have to do this. One thing with these problems, I try not to make them build too much on each other, but you can't have really 10 standalone problems because it takes just too long to develop 10 standalone scenarios in a test situation. So granted, this one builds on itself, but little tips like I mentioned previously. If you came up here and this one was positive, and then you get a negative number for this, you know you've got a mistake somewhere and you need to go back and sort that out. But I can be somewhat confident in my answer. I got a positive here and a positive here. At least that's working out. So I can say when I put V open circuit in there, which is the open circuit voltage, 3.33 volts, divided by the short circuit, which is 10 milliamps, and be real careful of the units now, because we're going to get units in k ohms, right? So we'll get 10 milliamps, so we'll get 333 ohms. I believe so, yeah. Because I divide by 10, which gives me 0.33, and then because I have milliamps, I'm going to multiply by 1,000, so I'll move that over 3. Yeah, that'll work. So got to be real careful of the units. So there we go. Answer C. And double check that for you. Yeah, somehow I was second guessing myself on that. No, that's correct, because you're going to move it. 10's going to move it one place there, and then the when you get rid of the have the milli in the denominator, you'll move it to the right 3 places. Good. The last one, what's the value of maximum power that could be supplied to terminals A and B? Well, we have a couple scenarios now. We could come over and we could look at the Thevenin source, which says that we have the open circuit voltage, 3.33 volts, in series with a resistance, 333 ohms. And we have the Norton model, where we had 10 milliamps in parallel with the resistance. And we know in each case that for maximum power transfer that the load resistance has to equal the Thevenin resistance. So this is going to be 333, and this would be 333. So here, if these two resistors are the same, this voltage across here is going to be equal to 3.33 divided by 2. And I could say then power is equal to, and remember we had that equation with the 4 in it, and I said I didn't remember it, because I always just drew the model like this, took the voltage as half the value, because when you square half, that's how you get the 4 in the denominator. But anyway, take the value at half the value, because we have an even voltage division. This is voltage division. And then use V squared over R. So what do I have? 3.33 divided by 2. I'm going to square that whole thing and divide by 333. Now this is in volts, and this is in ohms, so I should just come up with an answer in watts. Let me check on that. So I get a real small number here, 0.0083. I'll multiply by 0.0083, which I'm going to multiply by 1,000, get in milliwatts. 8.325, yeah, 3 milliwatts. I have that answer? Yeah, right there. Now, would I have got this same answer in this one? I think that's the way I actually did it in the solutions, but let me double check that. Again, the current, we've got 10 milliamps coming up to this point, right? So how's it going to split? Well, 5 milliamps are going to go there, and you're going to have 5 milliamps there, right? So we can use our old friend, powers equal to I squared times R. So I have 5 milliamps, 5 times 10 to the minus 3. So I'll work in amps. And then the resistance is 333. So let's see what I get there. Better square that, huh? So 0.0083. So when I multiply by 1,000, this being watts, when I multiply by 1,000, 8.33. Yeah, milliwatts. So same answer. Good. So lots of different ways. Like I said, I did it with the Norton model and the solutions. You can do it with the Thevenin model. Probably the biggest stumbling block here is the units. Be really careful of your units as you go through this. Well, let's see. That's page number 3. We'll move on. Look at page number 4. So typical op-amp circuit, we're going to assume linear operation. We're taking as V1 is 1 volt, V2 is 2 volts, and V3 is 4 volts. And you have to be really careful the polarity of this thing. Put a little note by that. Polarity's flipped over on that one, or I shouldn't say flip, but just opposite of what we sometimes usually see. Oftentimes the positive's on the top. Nothing wrong with this at all, just something we need to take into account as we go through this. R1, 2, 4, and 5, 1, 2, 4, and 5 are all 1K. And R3, the feedback resistor, is 4K. And we're asked a variety of questions here. So in doing this problem, I mean, the first thing we're looking for is this, find V naught. And these problems always start the same. We look at this node up here. This is all the same point, isn't it? And I could take this as V1 is probably not a very good designation for this, so maybe I'll call this VA. Maybe I'll call this VB. And what could we say about, a little better pen here, so I'll maybe do it. What could we say about this current here? We could say that's I minus, and this one here, I plus. Okay, so with linear operation, we know that VA is equal to VB. Have no idea what that's equal to, but I do know they're the same. Further, I know that I minus is equal to I plus is equal to 0. We know that that's equal to 0. So what I'm going to do is I'm going to do a Kirchhoff's current law at A, at this node right here. So I could say, and I better put some currents in there, I'll just put these leaving, assume that one's going that way, I1, I2, And we'll call this I3, or we could call it I feedback. You can put them, I mean, if you put your current going in, you'll have a negative associated with it, but when you then figure out what that current is, yours will differ from mine by a negative sign, and it will all work out as long as you're consistent. But I've got the currents all leaving, so I could say that I have I1 plus I2 plus I3 plus I minus, so that's what's leaving this node right there, is equal to 0. Obviously they can't all be positive, so one of them probably is negative, but that's okay. We know this I minus is 0. So then I could talk about I1. So I need to find the voltage like that. That's going to be from there to there, which we would normally say would be minus this source, but because they're polarity, I'm going from negative to positive, so that's a gain. So I'll have 1 volt plus VA. I have to divide by 1K plus I2. What's I2? I2 is going that way, so I need to find the voltage like this, don't I? Which is going to be from there to there, which is that minus 2. So I'll have VA minus 2, because I go minus 2, and then back up there, VA minus 2 over 1K. Plus I3. What's I3? Well, I've got to go like that, don't I? So that's going to be minus V naught, and then I'm down here because I've gone from there to there. From there to there is minus V naught, then back up there is VA, and good thing we got the unknown we're looking for in there. V naught, VA minus V naught divided by, this one is 4K, is equal to 0. So if I multiply everything by 4K, I get 4 plus 4 VA plus 4 VA so 4 VA minus 8 plus VA minus V naught is equal to 0. Okay, I think I'll double check my work there. 4 VA. Yeah, I think we're good. So we could tidy this up a little bit. What do I have? I got 8 VA, 9 VA minus V naught is equal to, let's see, I have on this side I have minus 4, so I'll go over here as positive 4. I could say then that V naught is equal to 9 VA minus 4. Okay, so if only I could find VA. Again, I get the classic situation, one equation with two unknowns. So I'm going to have to, I've used this one already, now I'm going to have to come up here and use this one, that VA is equal to VB. So let me look at this little piece of circuit right here. This is our reference ground. This is 4 volts and 1K. And right here is VB, that's the voltage at that point with respect to our reference ground. And then over here, normally I would say that you could not use voltage division across here, but the neat thing is this one, this current, if this current is not 0, you can't use voltage division. But what do we know about I plus? It's equal to 0, isn't it? So effectively, that branch doesn't exist, and we have our classic situation where we have voltage division. I mean, we've seen this many times. You have the source, you have a resistor like this, and a resistor like that. That's exactly what we have here. I mean, as long as there's no current going this way, as long as this current is equal to 0, we have voltage division. So we could say then that this voltage, which is VB, is going to be equal to the total voltage 4 volts times this resistor, which is, what was that, 1K? 1K divided by the sum of those two, which is 1 plus 1. That's K. The K's cancel, and I come up with 2 volts, right? So VB, therefore, VA is equal to 2 volts. So when I put 2 in here, substitute that in, I come up with what? 14. V naught is equal to 14 volts. We said that usually has to be between our plus and minus VCC. We weren't told that it was between there. We're assuming linear operation. We weren't told what minus VCC was and what positive VCC was. But I said usually it was somewhere between about 10 and 20. So we're going to be using 15 in the lab. So this fits the bill fine. I think we can be pretty comfortable and confident with that answer. And we're going to select B here. 14 volts. Now, the next part of this which builds on this is, given this circuit, everything remains the same. What is IX? Well, where in the world is IX? IX is right there. So if I come down to this diagram here, there is IX, isn't it? There is IX. Okay. Maybe I think I can just probably use this diagram here. Well, this current is going like this, isn't it? So I could say that IX is equal to minus VB divided by 1K, right? Minus VB over 1K. I'll let that sink in here. Where'd the negative sign come from? Well, remember when we first studied Ohm's law, we said if we had this voltage here that was positive and negative, that was because of a current that went this way. Ohm's law said that V is equal to I times R, right? Okay, so the current was going to go from positive to negative. Well, with this here, with VB, we have said that this is positive and this is negative, right? So would we have the current going from negative to positive? No, that's how we ended up with a negative sign. You could also think about this. I think this is how I did it in the solutions, like this. Again, because this was equal to 0, we can say this. So if I wanted to figure out what this I was, what's that going to be equal to? Well, it's going to be simply equal to this voltage here, VB, divided by that 1K. Okay? And which direction is IX? IX is in the opposite direction of that. So IX would be equal to minus I. Okay. So when you get that, what do we come up with? We have minus 2 volts divided by 1K ohm, which is minus 2 milliamps. Answer A, minus 2 milliamps. Well, before we leave this problem, again, looked like a fairly daunting problem when we first opened the page to it, but we tackle all of these op-amp problems the same way. We assume linear operation. The currents going in here are 0. The voltage at this node here and this node there are equal to each other. We do a Kirchhoff's current law here, and then we oftentimes use this other one to find that voltage. So very same process. Sometimes it gets muddied up with a voltage division or something, but always the same process. So here's a little circuit. Looks a little bit like the mesh circuit that we did in lab. We use the following circuit. Take Vs equal to 50 volts. I guess we only had one source in lab, didn't we? So, but we're probably going to end up doing some mesh analysis on this. So we got 50. This is 2 amps, R1, 2, and 3. 2 and 3 as 1 k ohm. And then R4 is 2 k ohm. And 5 and 6 is 1 k ohm. And what I did is I reduced this entire thing. I said, well, if I'm going to do mesh, I'll have a mesh here. I'll then have a mesh around this. And I don't want to have a third one. You could have a third one if you wanted to. But what I did is I said I reduced this to one single resistance, where I had 1K plus 1K, because those are in series. And then I put that all in parallel with 2K, right? Product over sum with 2K. So you got 2K essentially in parallel with 2K, which gives you 1K in the end. So I end up with 1K there. So now I'm going to say that this is I naught. I'll go ahead and say that this is I1. And I'm going to go ahead and say that this is I2. And we're looking for the power dissipated in R6. Well, if I can figure out what voltage we have across here, which is just going to be I2 times this 1K, then I can divide that between 1K and 1K. I do V squared over R. So what do we want in part 8? Part 8, what's I naught? So yeah, finding I2 and I naught are going to be important. We're essentially looking for this. We're looking for that. So let's go ahead and do some mesh analysis. The equations that I would look at then would be going from there to there. That's a gain of 50. So I'm going to say minus 50 plus, what do we have? I naught, or 1K, times I naught minus I2, plus 1K times I naught minus I1 is equal to 0. So that's one of my equations. Double check it here. So that's an equation. Then I can't go through this current source because I don't know the voltage across that current source. So what I'm going to have to do is I'm going to have to take a path around here. So let me do that. I could say, in doing that, that I have 1K times I1, it's right there, plus 1K times I1 minus I naught, plus 1K times I2 minus I naught. This is I2 going through here, minus I naught. Then over here, remember we replaced this whole mess with 1K, so that would be plus 1K times I2. Gets me back down to the ground state. We already took care of that one, so I can say that's equal to 0. So that's our second equation. I have 3 unknowns, so I need another equation. There exists an equation here relating I1 and I2, because I1 is going like that. I2 is opposing it, so I could say that I1 minus I2 is equal to 2 amps. So there is my 3 equations. In the solutions, I go through actually doing a substitution. So if you didn't have a matrix solver with you, you can see that. Making a substitution with this equation, putting it into these, and then adding those equations together. Probably a little easier if you just go through a matrix equation. So what would our equations be? Our equations, if we were to put them in, prepare them for matrix form, would be I1 minus I2 is equal to 2. That's probably the easiest one. And then if I look at this, how many I naughts do I have? I have 2K I naught minus 1K I1 minus 1k I2 is equal to 50. Is that right? 50 goes to the other side. Yes. Okay. And then lastly, what have I got here? I naughts minus 2k and I1s. I1 plus 2k I1 plus how many I2s? I2 there plus 2k I2 is equal to 0. So what I'm going to do then is I'm going to multiply those two equations by those last two equations. I'll just multiply them by 1,000, and when I put them into the matrix, maybe I'll jump over here, grab a clean sheet of paper. So this is 6, and we'll call this 7. So looking at those equations, I could say that I have 0 I naught, and then 1 I1, and minus 1 I2. So I'm building a matrix that looks like this: I naught, I1, I2. So you could think of this as the I naught column. We usually don't label them like this, but I naught, I1s, and I2 as far as the coefficients go. And then that's going to be equal to the right-hand side of the equation. So we'll have 2 over here. Like I said, I multiplied everything in this second equation by 1,000, so I have 2 minus 1 minus 1, and I didn't multiply by 1,000, I divided by 1,000, didn't I? So divide by 1,000. So when I do that, then I end up with what? 0.05. And finally, this one I also divided by 1,000. So minus 2 and 2 and 2 is 0. So that remains the same. Let me double check that with my work, make sure I don't lead you astray here. Yeah. Yeah. Okay, so when you get done with this, throw it in your calculator. You're going to come up with the above solutions. I naught is 0.05, and that's amps. I1 is equal to 1.025 amps, and I2 is equal to minus 0.975 amps. Okay, so does that work with the solutions that I did when I did the solutions to this? Yeah, 975 milliamps, 50, yes, 50. So, good. Well, where were we? We're back over here. What are we looking for? The power dissipated in R6, right? So if I find that I2 from matrix, I2 is equal to minus 975 milliamps, or 0.975 amps. What can I do? I could say then that this voltage across here, that the voltage across there is equal to, what's that going to be? V would be equal to minus 0.975 times the resistance, which that whole mess was 1K ohm. So I come up with minus 9 975, right? Volts. Grab my calculator here, get ready. So then if this is 1K and that's 1K, what is this voltage? The voltage across R6 is going to be equal to, it's an even split, 975 or minus 975 divided by 2, right? (487.5), negative 487.5. So I could say then that power is equal to V squared divided by R. So I've got minus 487.5 squared divided by the resistance, which is 1,000. So I got 237.6, we'll say 238, and that would be watts because I'm using the ohms. 238, right there, D. Good. Little, seems like a lot of voltage there, but remember we've got 50 volts and 2 amps. 2 amps is a pretty good sized value in a circuit like that, so we would expect that this could be a fairly high voltage number. I think the other way that I did this in the solutions, and I won't belabor it here, but I found this I2 and then I split that between there and there, which would be an even split, wouldn't it? That would be just that 0.975, negative if you want, divided by 2, isn't that? Because this is 2K and 1K and 1K is 2K, so the amount of current going through there. So then what you can do is you can square that and multiply it by 1,000. What do you come up with there? Come up with the same thing. So, good. So we've got that. 6, 7. I'll leave that matrix there for you to look at. And look at on the PDFs. And what do we have with 8? What's I naught? Oh, that's an easy one. I naught's equal to, right there. Found that with the matrix. 0.05 amps, which would be 50 milliamps. We have a 50 milliamps in there. Yep, right there, B. See page number 6 and 7. I don't know that we need to spend any more time on that. So 50 milliamps. Good. Well, our last problem looks like a throwback to the first exam, which it is. Really just, again, concentrating on node analysis. You got to be able to do node analysis, so don't be surprised if you see another one of these problems. Looks like, hey, that's off the first exam. Well, testing to see if you know node analysis. We got V1, we've got V2. We could, what are we looking for here? We've got this that's 50 volts. What's our current? 200 milliamps. Be real careful with that. R1, R2, R3 is 1K ohm. 1K, 1K, 1K. So if I'm using Ks, I think I'm going to leave that milli. I might have been tempted to say that it's 0.2 amps, but I think with the Ks, I'll leave this as milli. What was, let's see, I've messed this up already. 1, 2, and 3 is 1K. And then R4 is 2K. Okay. Used to be when we did tests that were partial credit, you'd try and mess up the problem in your favor. So you'd recopy the problem, maybe change something, make your life a little easier, and then hope to get some partial credit on it. But not so much on multiple choice here. I guess the good news is you can just take a blind guess and maybe get it right, but no partial credit. So what we need to do is we need to do Kirchhoff's law here. Let me I'll be consistent with the currents I did on the solution. I1, I2, I3, and then I'll have I4. So I could say if I do Kirchhoff's current law at node 1, what's that going to be? I1 plus I2 plus I3. I1 plus I2 plus I3 is equal to 0. Obviously, we couldn't have currents all coming out of something, so one of these is probably, one or more of them is probably negative, but that's okay. And we're also going to need what? We're going to need a Kirchhoff's law here, because I guarantee we're going to come up with one equation, two unknowns, and so we'll need another equation. We're going to need to do Kirchhoff's current law at 2, which is going to give this I3 going in and 200 milli going in. So I'll say that I have I3 plus 200 milli. Well, I might not write the amps. I do always have the milli because that's 10 to the minus 3. So those are going in, has to be equal to I4 leaving. So make my substitution. I think this is where people have problems. What do I have to do? I have to get from there to there. So I've got to go down here, minus 50, then back up there, V1, right? So V1 minus 50 divided by 1K. How about I2? I2 is easy. I just have to do this V1. V1 over 1K. Plus, and again, if you don't understand that, remember when we did Ohm's law on this, we had this again even on this test. If we have some resistance here and we have some current I, it's going to induce a voltage that is positive and negative. V is equal to I times R, right? That's Ohm's law. So the voltage has to be this opposite direction, has to be positive and negative. That's V1. V1 over 1K in that case. Then I3. What do? I take the head, V1, and subtract the tail, V1 minus V2 divided by 1K. Or you could say you go down there, which is minus V2, and back up there, which is V1. It's equal to 0. I multiply that whole thing by 1K, so I have, what, 3 V1 minus V2 is equal to 50. Is that right? So we said we'd have one equation with two unknowns. Good thing we wrote this equation over here. Well, what's I3? Well, no need to reinvent the wheel. We have I3 right here. V1 minus V2 over 1K. And we've got plus 200 milli is equal to I4. I4, what's that? Well, I4 is going like that, so I just need to find that voltage there. That's V2 divided by 2K. So I multiply this whole thing by 2,000. So I get 2V1 minus 2V2 plus, if I multiply 200 milli, 200 times 10 to the minus 3 times 2K, 2 times 10 to the 3, I get to cancel those, and I end up with 4, don't I? So 4 is equal to V2. So I have 2V1 minus 3V2 is equal to minus 4, right? So, oh, I still got this 200 here. I forgot those. Yeah, 200. So this should be 400, shouldn't it? There we go. Am I okay now? Yeah. Okay, so this would be 200 times 2, 400. Very good. I'm going to double check that. Okay, so two equations, two unknowns. You put them into a matrix solver. You could do substitution. What are we looking for? We're looking for V1 and V2, so I don't know if there's any real advantage substituting one way or another. I think I might. Let me grab a last piece of paper. This is 7. This is 8. This was 9. Looks like we get to page 10 here, don't we? So those are our equations. Why don't I multiply this one by 3 how did I do the solutions there? Yeah, that's how I did that. That's probably the easiest way, so I'll just stick with that. So if I multiply this one by 3, I've got 9v1 minus 3v2 is equal to 150. And if I add it, and it's not going to add very well, I've got to do one more thing. If I add it to this one, 2v1 minus 3v2 is equal to minus 400. What would I like to do? I'd like to get rid of this, so maybe I'll multiply this last equation by a minus 1, so minus, plus, and plus. So now I have those canceling, and I get 7v1 is equal to 550. So v1 is equal to 550 over 7. I have to go over a calculator. I don't think that's a nice one. 78.6 volts. We have an answer there for V1. 78.6. Great. That's looking good. That's probably a good news. I mean, you hate to get to this one here. We've talked about none of the above. That's usually not a good guess. Once in a while, you'll get right with none of the above, but usually I wouldn't. I'd usually try and sort it out between the other 4. Well, let's finish up then. If I have that V1, I could say that I have 3 times V1, which is 78.6, minus V2 is equal to 50. So V2 is equal to 50 minus 3 times 78.6. So V2 is equal to 185.7, let's say 186 volts. Do we have an answer for that? Yeah, 186. So that's probably pretty good news. So that problem was not particularly difficult. You could have easily, and people that were successful in the last test did one like this successfully. It's an important skill. We're going to see it more this term. We're going to see it more next term. So you got to learn that. Taken quite a while to go through this. Hopefully that's an advantage. I think if you're moving through these problems on the test, you're going to go through them quite a bit faster because you're not showing multiple ways of doing things and trying to explain that as you go. Well, again, I encourage you to go to the website, print out the exam, and try it. Even if you maybe got through it last time, you got 6, 7, 8 of them right. Print it out again and sit down. Give yourself maybe not an hour, maybe only 45 minutes or something. See if you can get through it faster and do better. Because like everything, it's just a matter of practice. Well, that wraps this up. Until next time, take care and thank you for watching.